share my screen. All right, so we're gonna get started. Today is the third week of Intro to Astronomy. I was saying this earlier, but we're gonna talk about a lot about how we study the universe, specifically how we look at the universe, the different tools we've developed to look at astronomical objects over the years, how we analyze the data that we collect, all of that. Also, to people who are actually in the meeting, I can't see you guys, I can't see the chat, but if you have a question, just say something or type it into the chat and I'll answer it afterwards, because I feel like you guys might have questions and I haven't really been able to answer them. So if you have a question, just say it or I'll answer it at the end of the meeting. Anyways, how was your week? I did this a little as people were coming in, but if you want to say something, I'll definitely look at it towards the end of the meeting. Anyways, so today we're going to talk a lot about light because that's the primary way we look at the universe. Really important concepts that I'm going to explain a little bit about. I'm also going to talk about telescopes and the two basic forms of telescopes that have been improved upon and added to over the years. Also observatories and how they work. And how they specifically collect scientific data that people use, and also stellar parallax, because that's a really important concept. It's a little bit complicated, but it's something that's really important to understand, and it's also pretty cool. Also, spectroscopy. I can never say this. Spectroscopy. Okay, spectroscopy. Sure. And that's how is a certain type of analyzing light that comes to us, and we can see what specific elements might make up some sort of a star or a planet or just astronomical objects in general, and also any sort of exploration and specifically analysis and ways people are thinking of beginning to explore the universe, all of that. Okay. So first of all, we're going to talk about light. So as we all know, light is a natural phenomenon that makes things visible to us. That's more of the human-centered definition of it. Specifically, it's a phenomenon that's made out of and caused by massless particles called photons that carry energy and travel throughout the universe. It's a pretty complicated topic. There's a lot of research that's still being done into this on the more quantum level. If you know a little bit about that, I'm only going to be getting into that a little bit, but it's a really interesting topic that you might want to look into when you're older and in university, because I'm a high school student and I don't really know what that's all about. But I hope that I can spark your interest in this a little bit, because it's important that we have people who want to study these things. Anyways, in the context of astronomy, the light that we're studying is emitted by stars, and it's traveling all throughout the universe. And specifically, it hits the Earth or any sort of astronomical observatory that we've created, and we look at it. Light that comes from stars is specifically emitted because of nuclear fusion. Like I was saying a second ago, light is made of particles called photons that are carrying energy, and this energy comes from nuclear fusion that happens in the center of stars. And this nuclear fusion creates a lot of energy, and this goes all throughout the universe, and this is how we see stars, up in these two images. Light, you might have heard, has a set speed limit, speed of light. It's about to look at that, it's about 300,000 meters a second, or 186,000 miles. 300 million, meters a second, and 186,000 miles per second. This is really important in helping scientists determine distance and properties of faraway objects, because we know that light has a specific speed that's supposed to be traveling. And we can, based on certain properties of the light, we can determine how far away things are from us. Yeah, for example, we know that the sun is one, I think I talked about this last week, but the sun is one astronomical unit away from us. So that means I think it's 93 million miles, and we know that light from the sun takes 8.6 seconds to reach us. So if we know that light has, oh, does someone have a question? Okay. If you have a question, just say, but I heard noise. I don't know. I want to be better about answering questions. Okay. Um, sorry. Anyways, light travels a specific distance in a specific time. We know this, and we know that it's true throughout the entire universe. So if we know how long something has been traveling for, we know how far away it is. And if we know how far away something is, we also know how long that light has been traveling to reach us. So the speed of light is a really important part of determining different features of the universe. So something that's weird about light that I was talking about a second ago, like the more quantum physics aspect of it, is that it is both a particle and a wave, which sounds very strange. And if you don't understand what I'm talking about, that is okay, because most people don't either. I mean, scientists even. But we can say that we think light is both a particle and a wave because it exhibits properties of both a particle and a wave, which makes sense. So the particle part comes from the fact that light travels through the universe in little packets of energy or particles called photons. So we know that that's true, but we also have seen things, seen light exhibit behaviors like refraction, diffraction, and interference. You might have heard of refraction and diffraction and also reflection in your science classes. And you might know that these are particles that waves exhibit. I'll explain a little bit about this in a second. Will I? I will. Okay. But because of these observed behaviors that we've seen in light, we can say that light is in fact a wave, which is strange, but it's also really important when we move on into like higher level topics. Anyways, light, because it's a wave, has wavelengths, and these wavelengths are determined by how much light energy has. So I don't know if I have a good diagram for this. Okay, here's my diagram. I'm gonna get my little pointy thingy thing. Okay, so the wavelength you can kind of see is the distance from, this isn't like a uniform wave, but this is a uniform wave. A wavelength is a distance from one point on the wave to another. So either from the trough, this is trough to trough, or crest to crest. And this wavelength is determined by how much energy a particle of light has. So if it has more energy, the distance between like the middle and the top is going to be a lot higher, which means that okay, I'll talk about this in a second. But yeah, light has certain wavelengths, and then that is determined by how much energy it has. Anyways, the weird wave-like properties of light are refraction, which is when light is like traveling through one substance or one medium, you would call it, and then it travels into another medium and it gets bent a little bit. And a particle wouldn't do that. Like if you, for example, threw a ball and then it was going through air and then it went through water, it would like travel in a downward curve, but that's just because of gravity. I don't know. Basically, when light is traveling through a different medium, it slows down a little bit and also changes direction. It's a little bit complicated, but basically, what's important for you guys to know is that a particle wouldn't do this, and that light, because it does something like this, that means that it is a wave. You also know, like when you put a pencil or an arm or anything else underwater, it kind of bends a little bit. It's weird, and you're like, what's going on? So that is because the light is refracting as it's going through the water and changing shape, basically. Diffraction is also a property of a wave. So when waves are moving, they travel like outwards radially. And then if they go through a small little, what do you call it? Like, in this example, it's like sound waves traveling through a small little area, the doorway, and then they travel through the doorway like at this angle, but then they end up radiating outwards. in like the same way that they did when they were first produced. And it's basically just when a wave splits up, and in light, it looks like light splitting up in a bunch of different ways. And this is a property of a wave that light happens to exhibit. And this is another reason why we can say that light is both a particle and a wave. And finally, one of the weirder and more important and more like quantum-y things that light does is that because it's a wave, it interferes with itself. So if we look at a little, this is called a sine wave. It's basically just a mathematical model of a wave. If we have two sine waves that are of the same like measurements, basically, they can add up with one another. This is what this diagram is showing, and they make one really big wave. And if they're like kind of the same measurements, but they're exactly opposite with each other, you can see how the high point on this one cancels out with the low point on this one, and they end up just adding and totally canceling each other out. So this process is called interference. And then over here, if we look at light, this would be light traveling as a wave, and then it goes through two more little slits in a wall. These slits do like diffraction, like I was saying a second ago, and they spread out radially, but then they also end up interfering with each other. And this is a part of a really important experiment called a double slit experiment. It's a little complicated to explain, and I wouldn't really be able to do a good job of explaining it, but if you want to look into it, it's called the double slit experiment. And basically it proves the theory that light is a wave, which is really important because we hadn't really had a proof before this like experiment and theory, basically. Anyways, on to the important part of astronomy. Because, like I was saying a minute ago, light has different wavelengths when it has different energy levels. And the wavelengths can go up from like the size of buildings. So like from one trough to the other trough, it's the entire length of a building between a light wave, which is kind of crazy. And then it goes from humans to butterflies to the size of a needlepoint, which is really tiny, even from a building. Then gamma rays are apparently all the way to the size of an atomic nuclei, which is really, really tiny. So we see light that is in between the size of a needlepoint and some life, some form of life. I don't know what form of life that is exactly, but we can only see this specific distance, like this specific size of wavelength, and this is what is called visible light, which makes sense. We can see it. And organisms, like specifically humans on Earth, have adapted to see visible light, and this is what we initially started observing in the universe. I have a diagram back here. This is the like emission graph kind of what the sun emits. You can see that on the ultraviolet, I didn't even name the forms of light, I will in a minute, but on the ultraviolet lens, or the ultraviolet side of things, which is the more energetic part of light, the sun doesn't emit as much as it does like visible light, and that's why humans have like mainly not why, but it makes sense that humans have evolved to like see visible light because the sun emits a lot of it, and it also emits some infrared, like larger infrared microwaves, TV, etc. Anyway, oh, that's important actually. Microwaves, TV, radios, they all use light. We say like radio waves, and we don't tend to think of radio waves as light, but they are light, which is an interesting concept. We just can't see it because the wavelength is longer than the wavelength of the visible light visible light region. So your phone, like your radio, your TV, all of that, all devices use like electromagnetic light, electromagnetic radiation, which is also called light, to communicate. So that's something. You probably knew that, but it's just cool if you didn't. Anyways, that's that. I feel like I was going to say something else, but I can't remember. Anyways, oh yeah, like I was saying a second ago, different wavelengths are important for astronomy because they reveal things that we wouldn't really be able to see with visible light. So with this specific nebula, And you can see in the visible light spectrum, it looks really cool, but you can see a bunch of different like other things that are happening to it with different forms of light. So like in the X-ray, you can see that there's some sort of thing orbiting itself and letting off light. Over here, you can see that gamma rays, oh, that's what I was gonna do. I was gonna say the longest type of wave with the longest wavelength, but also the lowest energy is called a radio wave. And then it goes microwave, infrared, visible. That is increasing in energy, and then increasing in energy even more is ultraviolet, X-ray, and gamma ray. Um, waves waves of light with the smallest or the shortest wavelength have more energy. Waves of light with longer wavelengths have lower energy. If you don't understand that, that's okay. I'll try and like point that out every time we talk about light. But anyways, over here you can see there's gamma rays, which means that this energy that is being emitted, or this light that is being emitted, is really high energy. Over here, it's like lower energy, so it's also cooler. Anyways, those are just a bunch of different bits of information that are revealed with different forms of light. And over here, this is actually nebula, or not nebula, it's Neptune. And you can see when it has, I think this is, these are radio waves, I think, or it's either radio waves or infrared light. But from the James Webb Space Telescope, you can see that Neptune is glowing and it has rings and it looks really cool. It kind of looks like Saturn. Anyways, here are some more like images, and this isn't actually visible light. So the light that you were seeing if you were looking in ultraviolet or mid infrared or far infrared wouldn't actually be these colors. Scientists have just like put specific colors onto the images so you can see them. Anyways, onto the part two, different types of telescopes that we have developed. So the first type of telescope that was invented in the early 1600s, I think 1608 specifically, it was called a refracting telescope. So I was talking a minute ago about how light refracts when it goes through different substances and different like shapes and stuff. So this type of telescope takes advantage of that, and it uses a lens to bend, which magnifies the light. So if you know like about a camera lens, if you like move the lens around a little bit, you can zoom in and out, and this is how this works kind of. It's using a bent lens to bend light into like into your eye basically and magnify things, which is really important and really helpful for looking at things that are really far away. The only problem is that images aren't very clear when you're looking at something so far away, but one solution to this is making longer telescopes. This gives more magnification, and also the clarity are related to the focal length. So like the length of the telescope, which is also like related to the lens. I'm not exactly sure how that works, but what this means in practice is that if you want a telescope that magnifies things more and is also clearer, you need to make a really, really long telescope. Like, I think this is like one of the longest in the world, refracting telescopes at least. And yeah, refracting and reflecting telescopes both work with visible light only, but they're really helpful for looking at things in our solar system and even things that are a little bit farther away than that. Anyways, here's a little diagram about how that works. So basically, light travels in, it goes through a lens, it gets bent, and it actually like inverts on itself. So if you ever looked through a telescope, you know that the light is actually flipped around, which is a little bit weird, but you have to get used to it. But yeah, and it goes into your eye and it's like magnified significantly, which is important. There's also reflecting telescopes, which are newer. They were still invented in the late 1600s, though. It collects light using mirrors and then bends the light a little bit and positions the mirrors and focuses the light into your eye. So for this one, it's really good at catching light. So this has an advantage so that it can see objects that aren't as like bright in the sky and it makes them brighter. And this one works so that if you have a bigger mirror, like the mirror on the James Webb Space Telescope, it's gigantic, you get a brighter and a clearer image. A little diagram over here. the light comes in, it goes onto a bent mirror, and then goes onto another mirror, and then goes into your eye. In this one, they both have their advantages and disadvantages. And then a catadioptric telescope combines mirrors and refraction, and it was invented in the 1930s, and it has a higher resolution and a higher light gathering ability because it combines the two approaches, and apparently it's really good for astrophotography. I don't know as much about this one, but yeah, I have a little for homework for you guys. I have a little game you can play to kind of look at the different parts of a telescope and how they work, because I didn't talk as much about that, but that might be really important if you actually want to go out and use a telescope yourself, which is cool. And I hope you guys check that out if you want to. Anyways, here's a little bit about how this kind of telescope works. Light goes in, light goes in from this side. It goes onto the correcting lens, which corrects any sort of imperfections or distortions caused by other lenses. I forgot to mention that's kind of a disadvantage of these two types of telescopes, specifically refracting. It can kind of bend and blur the light a little bit. That makes it hard to see faraway objects. But this kind of telescope attempts to correct that. Anyways, we're going to talk a little bit about observatories. So I didn't talk about this as much. I think I talked about it last week, but the atmosphere actually stops some wavelengths of light, actually a lot of wavelengths of light, from getting into the atmosphere. So if you wanted to observe faraway objects that are emitting X-ray light on the surface of the Earth, you actually wouldn't be able to do that because the atmosphere blocks out a lot of electromagnetic radiation. We can, of course, still see visible light. This is what the types of telescopes I just talked about are really good for. And you can also see a little bit infrared light and also radio waves, but you can't see that much infrared or microwave light. And you also can't see gamma ray, ultraviolet as much, or X-rays. So when you go into making observatories, you have to first pick out what kind of light you want to observe, and then you would pick out where you want to put the observatory based on what light you want to observe and what light gets canceled out by the atmosphere. And so then observatories do things for scientists. So they collect all kinds of data about the atmosphere, about the universe and solar system. So because obviously we can't go to a place like, I don't know, in the Andromeda galaxy, the only way we have to look at it is through light. And light can tell you so much. I'll talk about that in a minute. But observatories do what you would expect. They collect data on galaxies and stars. A really cool thing that phenomenon with space is that the farther away you look, you're actually looking into the past, because I'll get into this in a minute, but the universe is expanding, which means that light that was emitted a long time ago actually takes longer than it would normally to get to us, because it has to travel through a universe that has gotten bigger since it was emitted. So it takes longer to travel across that distance, because that distance is perpetually getting bigger. So the farther you look into space, the farther you're looking into the past, which is really cool. Anyways, we're using all of this data to figure out the origins of the universe, which is a pretty bold mission, but we're trying to do that. And also other space mysteries like dark matter, dark energy, what neutrinos are, also a lot of particle physics that's also really interconnected with astronomy. I'm not going to talk about that as much, but it's cool. Anyways, there are a bunch of different types of telescopes. So like I was saying a minute ago, different wavelengths of light are emitted from different objects, and they reach different parts in our atmosphere depending on how they interact with the atmosphere. I didn't say that, but anyways, radio telescopes. So radio telescopes, if we look at the diagram back here, radio waves can reach the ground. So radio telescopes are generally located on the ground. They look like dishes. You can see them here. They look through generally like dust clouds in outer space and basically objects that are emitting lower energy light. So generally also cooler objects. They are cool, but I mean like cool in temperature. Okay, anyway. Microwave telescopes are also a thing. As you can see on this diagram, microwave light would be around here, and microwaves can't quite reach the Earth. Maybe some over here can, but not really. So microwave telescopes generally tend to be built in space, in the atmosphere, and at really high altitudes. And they study the cosmic microwave background radiation, which is this little thing over here. This tells us a lot about the origins of the universe. I'm going to do a class about cosmology, and I'll talk a lot about that. But this is old light that comes like from the very, very, very beginning of the universe, and we use it to do things. Anyways, infrared telescopes are also a thing. They tend to be in space and also on mountaintops when they can reach it. And they study, again, like dust clouds and older objects. I'm pretty sure the James Webb Space Telescope is an infrared. I'm not entirely sure though, but I know it's studying really old galaxies and things like that. And then, of course, we have optical observatories. These basically just have the gigantic, like, refracting telescopes that I was talking about a minute ago. They study any object that's emitting visible light. And also, X-ray telescopes are in space, and they study hotter objects because the light that they're studying has more energy than other forms of light. So, yeah, as you can see over here, like X-rays don't enter the atmosphere, so anything higher than visible light and like lower level ultraviolet light tends to be in space. So if you've ever thought like, well, why are telescopes and like things like the Hubble telescope or the James Webb Space Telescope like in space, why can't they just be here? It's because the forms of light that they're looking at actually don't get to Earth, and it's a lot better to be in space, and also there's less light pollution and stuff like that. But anyway, so one thing that's really cool is the Event Horizon Telescope, which was used to take a picture of a black hole of M87, I think that's the name of it, this black hole. So basically, what I was saying a few minutes ago about how if you want something to be like clear in detail, you need like bigger telescopes, basically. So scientists really wanted to take a picture of a black hole, but they couldn't really figure out how to get a telescope big enough to like get a really good resolution of the black hole because it's so far away and it's so tiny. So they decided, well, if we want to take a picture of a black hole, we need a telescope that's the size of the entire Earth, which is a little crazy. But then they're like, wait, maybe it's not so crazy. What if we put a bunch of different telescopes all around the Earth and made a telescope that is technically the size of the entire Earth, and we put all that data together and we took a picture. And that is what they did. And this is like such a crazy idea when you think about it, but also it makes a lot of sense. So as you can see, they took 8 different telescopes. They compiled all the data, and they took this picture of this black hole, which is really famous, and it's also so important in the field of astronomy. The fact that they were able to take a picture of something that was so far away. Anyways, that's just a cool little project that I think needs to be talked about. Anyways, here's another little image of what types of light can reach that atmosphere and like where telescopes are positioned based on the type of light that they're studying. As you can see, okay, yeah, James Webb is an infrared telescope, and Hubble is actually studying visible light, but it's like in the space. Anyways, there aren't like as many telescopes that are studying higher energy light, but 2 are the Fermi and Chandra telescopes. At one point I knew what they were studying, but they're studying things that are probably hotter and like emit higher energy light. Anyways, yeah. Here's another picture of a bunch of different telescopes and where they're positioned. And here you can see like another attempt at making a bigger telescope by having a bunch of like smaller telescopes all positioned and working together. Anyways, one concept that's a little bit hard to explain, but is also really important is stellar parallax. So basically, um, the Earth moves around the sun once a year. We know this. So if you want to like see how far a star is away, you can use something